Hello. In the last video we introduced the Poisson process, which is a continuous version of a Markov chain. Markov chains have discrete steps or stages. At each step there is a transition. For the Poisson process, we associated each step with a very small time interval. So we chose a large number n such that n transitions corresponds to one time unit. Now each transition has very small probability, so over n transitions the chain is bound to change, but I tried to emphasize that the Poisson process is in some sense a limit of the usual discrete Markov chain. All right, now we're going to generalize. If you recall, the Poisson process had a constant probability of transition no matter what the state was and no matter what the time was. You can see that right here. The probability that x of t plus dt equals n is equal to 1 minus lambda dt times the probability x of t equals n plus lambda dt times the probability that x of t equals n minus 1. The two terms on the right correspond to two different events, which in fact form a partition of all possible events which correspond to this eventuality. If x of t plus dt equals n, there's only two possibilities. Either there was no transition in the interval t to t plus dt, or there was a transition from t to t plus dt. This term corresponds to the case where there's no transition in the interval t to t plus dt. This term corresponds to the event that there is a transition in the interval t to t plus dt. Now, if you recall our conditional probability formula, it was something like this. Probability of B is equal to the sum of probability of B given AI times the probability of AI. And that's exactly what we have here. We have two different events, xt equals n and xt equals n minus 1, which form my partition. I can call this A1 and this A2. And this is the probability that I end up in state n at time t plus dt, given that I was in state n at time t. So this is the probability of B given A1. This is the probability of B given A2. So this is just my conditional probability formula. So in the next two sentences, I just say the same thing in words. You can read that and reinforce that concept. Now, in this case, as I mentioned, the transition probabilities were independent of the state n and independent of t. So in this video, we're going to look at the case where the transition probabilities are not independent of the state. However, they are still independent of t. The transition probability now depends on the state. So the only change we need to make is, instead of having lambda dt, as we did before, we now have lambda of n dt, where the lambda depends on n. And lambda of n minus 1 times dt. Now why do I use lambda of n minus 1 here? Well, because this is the event that xt equals n minus 1. So to move from n minus 1 to n, the transition probability should correspond to the state n minus 1. Similarly, in this case, I was in state n at time t, so the transition probability here should correspond to the transition probability for state n, because I'm talking about moving from state n to state n. What we would like to do now is turn this into a differential equation, just as we did with the Poisson process. Now, In the Poisson process, we had a derivative with respect to time. So derivative with respect to time means you have a function of t plus dt minus a function of t divided by dt. So here we have the function of t plus dt. Where's the function of t? Well, here it is right here. And notice that this multiplies a 1. So I'm going to break this term up into 2 and distribute. This is going to be p of xt equal n, then minus lambda of n dt times p of xt equal n. And I'm going to move this term to the other side of the equation. So what's left is this minus lambda dt times p of xt equals n. That's the first term here. And then I have the second term maintained as before. Now I can take the limit as dt goes to 0, and I have the usual limit for a derivative, and that gives me my equation. You can compare. The only change is that I have changed this limit to a derivative. And this is the same as equation 2.13 in Kasumu's book. So we'll be seeing this process several times. In fact, there are other processes like the pure death process and birth-death process. But the reasoning is exactly the same. It's important that you come to understand how to derive this equation. So I'll be letting you derive those two equations. We'll see how that works out later. Now, we're looking at a special case where lambda of n is proportional to n. So let me make that very clear that this is a special case. Well, in this special case, we have lambda of n proportional to n. Now, this is quite common in population applications because usually the number of births in a population is proportional to the population. You have more couples, you're going to have more births. That means that my lambda of n is written as n times lambda, where lambda is some constant, and this is called a linear birth process. Now, as before, what we have here is not a single equation, but an infinite set of equations. And I can arrange them as an infinite vector. I mentioned before that a vector can be associated with a polynomial. Well, an infinite vector can be associated with an infinite series. How does that work? You multiply the nth term by s to the n, where s is my polynomial variable, and summing. Again, there's nothing sacred about s. I could use x or I could use z. But what I'm doing is I'm converting an infinite vector into an infinite series. And this allows me to make a unified equation, a single equation, that expresses the entire system of vector equations. Now, to make more clear what's going on, let me repeat the equation above and put in the linear birth terms. Okay, so I've inserted the equation here. You can see the only change between this new equation and the equation I had before was I'm writing lambda of n as lambda times n. And lambda of n minus 1 is lambda times n minus 1. The birth rate is linear, proportional to n. Now, if I multiply all the terms in this equation by s to the n, I get a s to the n here. I should multiply this term by s to the n. Now, what I did was I split this up. I multiplied by s here and s to the n minus 1 here. And I actually put the n on the other side. Now, you can see that this term here is just this term rearranged, multiplied by s to the n, but the s to the n is split into two parts. I'm going to do the same thing here. I'm going to multiply this term here by s to the n. So I move the n minus 1 after the piece of n minus 1. And I multiplied by s to the n, but my s to the n is split into two parts, s squared and s to the n minus 2. You should know your exponent rules that this expression, s times s to the n minus 1, is actually equal to s to the n. And similarly, s squared times s to the n minus 2 is equal to s to the n. So we multiply, and then we notice something. This ns to the n minus 1. This may be familiar from differential calculus. In fact, this is the derivative of s to the n. Now that's very nice because then I get rid of this n outside of the exponent. That's very nice. Now similarly, this also is a derivative. This is the derivative of s to the n minus 1. So I can replace these expressions here and here with derivatives. At this point, I'm going to take the sum over n from n equals 0 to infinity. Now, one more thing to notice. In fact, the term here, this Pn of t, does not depend on s, because t is a different variable from s. So I can move this p sub n of t inside the derivative. Similarly, I can move this p sub n minus 1 of t inside the derivative, because it does not depend on s. So that's what I've done here. Notice I can't move the s inside the derivative because s is a function of s. And that would change the derivative value because of the product rule. Now I'm ready to sum over n. Each one of these is going to be considered as one term in a power series. So I'm going to replace p sub n of t times s of n by the sum. So that's just like summing all these equations together. Now notice something. Here we have n equals 0. Here we have s n minus 1. In fact, when n equals 0, this term is 0. But that's a little bit sloppy. But we don't have to worry about the case n equals 0 for this term here. So as I said, I replaced the term p sub n of t times s to the n by its sum. And I'm going to call this power series k of t and s. It's a function of t and of s. Now when I perform this sum, if I take the sum from n equals 0 to infinity, that gives me k of t and s. I'll get the same thing here, k of t and s. Then I'll get the same thing here, k of t and s. Don't worry about the term when n equals 0. That's just going to give me 0. If I sum the rest of the terms, I'm going to get k of t and s. You can combine these two terms because they both have the same derivative of k of t and s. And you get this result from Kasumu's book. So this is a partial differential equation. The function involved has two different variables. How do we solve this? Well, in fact, there's a common technique for solving partial differential equations. It's called separation of variables. So we first assume that the solution of k of t and s is a product of a function of s times a function of t. Now, if you do this, then in fact, you can solve this equation for f and for g. And that's what this exercise is leading you through. So we're assuming that k of t and s is a function of s times a function of t. That means that we can replace k of t and s with f of s times g of t. Now we'll have parts of the equation that involve s and parts of the equation that will involve t. We want to put all the parts that involve s on the right-hand side of the equation and all the parts that involve t on the left-hand side of the equation. Now, if you have constants that don't depend on s or t, it doesn't matter which side of the equation you put it on. I'm going to put all the s-dependent expressions on the right and all the t-dependent expressions on the left. So the left-hand side is a function of t only, and the right-hand side is a function of s only. Now, here's where the clever argument comes through. Since the left-hand side is a function of t only, it's not a function of s. Right, since the right-hand side is a function of s only, it doesn't depend on t. Now, since they're equal, these both quantities cannot depend on either s or t. So they must be constant, because s and t are my only two variables. Very clever. So I can set both of these sides of the equation to a constant which doesn't depend on s or t. Now what that's going to do is give me two separate equations. It will give me the t-dependent part equals c and the s-dependent part equal to c. And you can use those equations to solve for f of s and g of t separately. Now we have assumed that the solution has this form, f of s times g of t. But we can go farther. Suppose I take any differentiable function of one variable. I'm going to use the letter big H to denote that function. And then take h of my product function. Take h of f of s times g of t. I want you to show that this function is also a function of s and t. This function also satisfies the equation 2 for t. This, in fact, is the most general solution to 214. So if we can get a solution to 214, we can find k of s and t, and then we can reconstruct its power series, take the coefficient of s to the n, and find the value of Pn of t. Very clever. We won't do those calculations in this video, but we'll have a chance to do these later. Okay, thanks for watching.